My dear student, colleagues, and all the viewers who are watching this program live from Facebook page, Physics Center, and School of Astrophysics and Astronomy, I would like to welcome you all to our International Physics webinar. So, good evening to all here in Bangladesh, and a very good morning to all those who are watching this program live from USA. Hope you are well and safe from Corona pandemic. So we are trying to adjust with this new normal situation. As you know that we are staying in a Corona pandemic situation, so it's very difficult for us to continue our continue our academic program inside the campus. We have to continue our online program. I think you have already come to know that the Department of Physics, Pabna University of Science and Technology, has started its online program, including online international physics webinar. We have successfully completed our 179 International Physics webinar. Today it's our 180th International Physics webinar, and today I'd like to welcome you all to a joint session between the Department of Physics, Pabna University of Science and Technology, and the Department of Physics and Astronomy, University of Nebraska, Lincoln, USA. And we have with us here today Dr. Martin Centurion, Sushan J. Rosowski, Associate Professor, Department of Physics and Astronomy, University of Nebraska, Lincoln, USA, and he has already connected with us. So I'd like to welcome our speaker. Sir, good morning and good evening to here, and thanks for joining with us. So, for those who are new, I'd like to inform you all that we have divided our webinar into three parts. First of all, we'll introduce our speaker with all of you, and then our speaker will deliver his speech, and at the end we have a discussion session. In that time, anybody can join with us, and you can also ask questions by commenting. I think you have already come to know the title of this today's International Physics webinar, that is the ultra-fast imaging of molecules with atomic resolution, and our speaker is Dr. Martin Centurion, Sushan J. Rosowski, Associate Professor, Department of Physics and Astronomy, University of Nebraska, Lincoln, USA. And we can see his educational professional background. He has completed his bachelor degree in physics, University of Michigan in 2006, and PhD in physics, California Institute of Technology from in 2005, and postdoctoral at the California Institute of Technology from 2005 to 2009, and also worked as a postdoctoral fellow at the Max Planck Institute of Quantum Optics. So you can see his professional experience. So he worked. Uh, he joined as a assistant professor at the Department of Physics and Astronomy, University of Nebraska in 2009, and so now he's working as an associate professor at the Department of Physics and Astronomy at the University of Nebraska, Lincoln. We can see his awards and honor, and this is the research in molecular imaging, ultrafast molecular dynamics, ultrafast electron diffraction. This is his booster ID, and his citation is more than 2000, and this is his publication list. So thanks all of your patience. Now it's time to go to our speaker. So sir, thanks again. It's your time. You can start your session.
Okay, thank you. Thank you for inviting me to give this seminar and to present my research. So I think we got the title down. So maybe let me explain a little bit what is the research that we do in my group. And our main interest is to understand how light is converted into other forms of energy at the level of single molecules. So how does a molecule absorb light and convert this energy into chemical energy by changes in the structure, or into mechanical energy, which is heat by vibrations? And this sort of transformation is very important for many different mechanisms. I hope you can see my pointer. So one example, for example, is vision and photosynthesis. So here we have the retinal molecule, which is in your eye. And after absorbing light, this molecule undergoes this change in structure, which then triggers changes in the properties of this molecule. And there's a whole sequence of events that follow, and then you can, for example, see some light hitting your eye. Now, This first part of the process is very fast. It takes place on the scale of hundreds of femtoseconds, and this reaction also happens quite efficiently. Another example is using molecules to convert and store solar energy. For example, this molecule uh, converts between these two forms, and this form has a strained structure, and you can store energy, you can absorb light, go to this more strained structure where energy is stored into the conformation, and then you can release this energy either by a catalyst or another photon. So it's another way of using molecules. And then another example is your DNA. So your DNA can be damaged by UV light, but the DNA bases, for example, thymine is one of those, can very efficiently convert this UV light into vibrations and into heat. And this is believed to reduce the rate of damaging reactions in your DNA. So different molecules either can trigger a reaction very efficiently or can try to avoid a chemical reaction by dissipating the energy. And this all happens in femtosecond timescales. And what happens is when a molecule absorbs a photon, that's a lot of energy for a molecule. And often what you see is that all this energy gets channeled into gets funneled into a specific channel, and basically avoiding all the other possible things that could happen. And the way to do that is to do it very fast. So if you can funnel the energy and go into a specific reaction channel very fast, you can do it faster than the dissipation time and faster than the time it would take to reach other reactions. So the fact that these reactions are very fast is coupled to the fact that they can happen very efficiently. And so we want to understand how these things happen, which means we want to be able to see them. And like I said, they happen on femtosecond timescales. So you need a camera which is fast enough to see them, but they also happen on atomic scales, right? We want to see these structures as they're changing. So we need to reach atomic resolution to be able to see what is happening. So our goal is to actually make a movie of this reaction as it's taking place. So we take a molecule and we want to understand the intrinsic response of molecules. So we look at isolated molecules. So that means we put a molecule in a gas beam where it's not interacting with anything else. And then we can trigger a reaction with a laser. So a laser is a very precise tool, so we can prepare the excited state very carefully, and we can prepare a specific excited state by adjusting, for example, the wavelength of the laser and the intensity of the laser. And then we need a way to probe this reaction, and we use electrons to probe the reactions, because with electrons we can reach atomic resolution. So this energy conversion takes place by movement of the atoms. So that is what we want to see. And there are two things that happen. So when you excite with the laser, the electronic configuration changes, and the nuclear configuration also changes. And the method that I'm going to describe is one which is good to look at the changes in the structure, so the motion of the atoms. And there are many other spectroscopic methods which can look at the changes in the electronic state of the molecule. So these two types of measurements are complementary. So I'm going to spend a few minutes to try to explain how our tool works, ultrafast electron diffraction. And then I'm going to tell you about two different examples. One is a proof of principle experiment that we show that this method works by looking at a coherent vibration in a diatomic molecule. In this case, this is iodine. And then I'll show you an example where we can follow a much more complex reaction as it takes place. So the idea is that we use electron diffraction to see the structures. And so what we want to see is we want to see resolved distances less than 1 angstrom. And we know that the spatial resolution of any imaging or diffraction is limited by the wavelength. So if you use visible light, you are limited to a few hundred nanometers. But if you use electrons, then you can easily reach wavelengths which are a lot smaller. For example, just accelerating electrons to 30 kiloelectron volts, you already have a wavelength of 7 picometers, so well below 1 angstrom. And then how do we use diffraction to see atoms? So this is the basic idea. This is the famous Young's double slit experiment. So we have an incident wave here, and this wave hits these two slits, and then you now have waves emanating from these two slits. And these two waves will form an interference pattern here on the screen, and the interference pattern looks something like this. It has bright regions and dark regions, right, periodically changing. Now the key point here is that if I measure the period of this interference pattern, and I know the wavelength of this radiation, and I know the distance from the slits to the screen, from a measurement of this interference pattern, I can calculate what is the distance between the two slits. So again, I choose the wavelength, and I choose this distance, and I measure this, and I can know the distance between the two slits. Now let's imagine that instead of two slits, I have a molecule, a diatomic molecule, which has two atoms. Then waves will be scattered from each atom and interfere on the detector, making again a sinusoidal interference pattern. And now again, if I choose the wavelength and the distance carefully, I can make this interference pattern to be on a macroscopic scale. For example, this can be on the order of millimeters, which I can easily measure. And then by knowledge of the distance and the wavelength, I can calculate what the distance between the two atoms is, which is on the order of an angstrom. So by carefully choosing all the parameters, I make a macroscopic measurement to know a microscopic distance. So I measure something on millimeters, and I know the distance between these two atoms, which is on the order of an angstrom. Now imagine what happens if I add another atom here. Then I'm going to have one interference from this atom, another interference from the other pair of atoms. So for every pair of atoms, I'm going to get a sinusoidal interference pattern, and then they will all are going to be superimposed on each other. But I can still, of course, separate them. So gas electron diffraction. So this technique has been used for a long time, with the first experiment in the early 1930s. Soon after the discovery of the electron properties, of the wave properties of electrons. And the reason is that it's very simple, and it gives you a lot of information about the structure of the molecules. So you make a gas beam with a molecule of interest, you cross it with an electron beam, and then you record the scattering pattern on a detector. Typically, these samples are very diffuse, so only a small percentage of the incident electrons get scattered. So there's a very bright beam in the center, which usually you have to block it to avoid saturation. So you see a lot of our scattering patterns have a dark region in the center, and this is just because we are blocking the incident electron beam. And to increase the amount of signal, we try to put a lot of molecules in the interaction volume, and these molecules are not interacting with each other, but we just have a lot so that we can increase the signal to a measurable level. This brings another issue, that because we have a gas of molecules are all pointing in different directions. So we have an ensemble of randomly oriented molecules. And so the end result of this is that instead of diffraction bars like this, you now get diffraction rings. You get circular symmetry here. And the contrast of the interference pattern is decreased, but you still can retrieve the relevant information. So we can typically express total scattering in terms of what we call an atomic scattering intensity and molecular scattering intensity. And we express this in terms of the momentum transfer. So this is the momentum transfer of the scattered electrons. Theta is the scattering angle, and lambda is the wavelength of the electrons. Now for small angles, this momentum transfer is just proportional to the angle. And mostly we are dealing with small angles. So you can think of this, if you like, as a representation of the scattering angle. Now, this atomic scattering is basically the scattering that you just get from individual atoms, so it does not contain any structural information. But the molecular scattering contains a sum of terms that look like this. So the Fi and Fj, these are the scattering amplitudes of atoms I and J. So heavier atoms have a larger scattering amplitude. And then S is the momentum transfer, and Rij is the distance between atoms I and J. And then again, you get this in the denominator. So you basically get a sinc function, but you get a sinusoidal modulation where the frequency of this modulation depends on the distance between atoms I and J. And if you have many atoms, you get a sum of many terms like this, and where the frequency of each sine wave depends on the distance between each pair of atoms in the molecule. So let me show you one example. So this is before we look at the diffraction patterns, we do some rescaling of the molecular scattering, and we generate this modified molecular scattering. And the reason for this is that the scattering amplitude decreases very rapidly with momentum transfer or with scattering angle. So the amplitude of the modulation goes down very fast as you move away from the center. So we do some rescaling, basically just to bring up these diffraction rings and make them more visible. So here we have an example from this molecule, and this is the calculated or theoretical scattering, and this is what we have measured. And this molecule, for example, has 2 carbon atoms in black, 4 fluorine atoms in green, and 2 iodine atoms here in purple on the 2 ends. And so because the molecules are randomly oriented, then the diffraction pattern has to have circular symmetry. And so we can do an azimuthal average, and we get a curve like this. And again, what this curve is a sum of sinusoidal patterns, and one sinusoidal pattern from each pair of atoms. For example, this two, carbon, iodine, all of them have an interference. So we can retrieve the distances, which we call the pair distribution function, by doing a sine transform or a Fourier transform of this signal here. So now the pair distribution function will have a peak corresponding to the distance between each pair of atoms. So for example, at 5 angstrom, we have one peak, which corresponds to the distance between the 2 iodine atoms. And then here there are several other atom pairs, but we see only 3 additional peaks. And that's because some of the distances are quite close, and the experiment, of course, has a finite resolution. So here there can be more than one distance under each of these peaks. So that's something that we have to deal with in the data analysis. Okay, but what we are interested is in the changes in the structure. So now we introduce also, so we have again our gas, our electron pulse, and we now introduce a laser pulse into the setup. So the laser pulse will excite the molecules, and then at a fixed delay time, we probe this with an electron pulse and record the scattering pattern. So I'll talk more about this later, but the electron pulse and the laser pulse have to be synchronized on a femtosecond timescale so that you can probe at a specific time. So you excite with the laser, you probe with the electrons, and you record a scattering pattern. Then you change the relative delay between laser and electrons and do it again. And so you do this many times, and then you have many diffraction patterns, and each one is probing a specific time after the reaction was triggered. And now what we do is, because there's a lot of background in this signal, so what we do is we generate a difference pattern. So in this case, we usually know already what the structure is in the ground state, what is the static structure, or we can determine it beforehand. And we generate these different patterns, and then we generate this different pair distribution function. So now we can just look, and for example, if there's a negative part in this pair distribution function, that means that this distance is missing. So something happened in the molecule and there's a missing distance, and if there's a positive region, that means that there's a new distance. And from this, we can try to reconstruct what are the changes in the structure of the molecule. And a lot of the early work in this field was done by the group of Ahmed Suwail in the late 1990s and early 2000s, where he developed an instrument where he could do these diffraction experiments with a resolution of a few picoseconds. And with this, he could determine a lot of transition state structures and look at a lot of reactions. However, the coherent motion of the atoms, which is what we are more interested in here, which is to see how the atoms actually move, this was still not within the range of the measurements because of the time resolution. And I should mention that Professor Sewell got the Nobel Prize in 1999 for his work in femtochemistry, where he basically introduced femtosecond lasers to study chemical reactions, and he demonstrated that one could see these coherent motions by looking at reactions with basically spectroscopic methods. Okay, so why was the temporal resolution in picoseconds rather than femtoseconds? Well, the reason is that there are two reasons. One is that electrons are charged particles, so you can generate a short pulse of electrons, for example, by hitting a photocathode with a laser and using photoemission. But these are charged particles, so they will very quickly push on each other and spread out, and this is called the space charge effect. So you generate a very short pulse of electrons, and then you propagate even a short distance, and the pulse will spread significantly. The second reason is that if you generate electrons, say at 30 kilo electron volts, they propagate with about 1/3 of the speed of light. So imagine now that this is your gas sample, and you try to set the delay between, let's say, the lasers in red and the electrons in blue. Because the lasers are faster, the relative delay between the two will change as the pulses go through the sample, and this change in the time delay will blur your resolution. And even for a thin gas jet, this effect is on the order of 1 picosecond. So how can we combat these effects to try to improve the resolution? So one way is to go to relativistic electrons. And here the space charge effect is reduced significantly. So here gamma is the relativistic factor. And also you can make the velocity mismatch much smaller by bringing the speed of electrons very close to the speed of light. And so with these improvements, you can now reach a time scale in the order of 100 femtoseconds, where you can see, where you can reach the scale where you can see the nuclear motion. So to do this, we went to SLAC National Lab, and we collaborated with the group led by CJ Wang and Ji Yang there, where they had an RF electron gun which can generate MEV electron pulses. This electron gun is similar to the one that drives the X-ray free electron laser, but here we just use the electron gun, and we have a femtosecond laser pulse which shines on the photocathode. Then the electrons get accelerated in an RF field to energies between 3 and 5 mega electron volts. Then we have some electron optics. Then we have our sample chamber here. Now here the the electron wavelength is very small, just in this case 0.3 picometers. So the diffraction angles are very small. So the detector actually sits about 3 meters away from the sample chamber. So this is a photograph of the setup as it was a few years ago. So here's the gun, here's a sample chamber, and then there are two detectors, a near detector and a far detector. And from the sample to the detectors between 3 and 4 meters. But the great thing was that with this setup, we were able to reach a resolution of 150 femtoseconds or less. So we did two proof of principle experiments. One was to look at a vibrational wave packet in iodine molecules. The other was to look at a rotational wave packet in nitrogen molecules. And I'll tell you now about the first of these two experiments. So in this case, we use a laser pulse with a wavelength of 530 nanometers to excite the iodine molecules, and then we use an electron pulse to probe this excited molecules. And to introduce a laser in and out of the sample volume, we use these mirrors with these Holy mirrors, which have a hole in the center for the electron to pass through. And all of this is, of course, it's inside of a vacuum chamber. And then we use a detector, and in this case, the detector is a phosphor screen, which has a hole in the center for the through beam to pass, and then only the scattered electrons get collected, and this get imaged into a camera. So the excitation that we're doing is we go here in blue, this dashed line is the ground state of iodine, and here's the nuclear wave packet in the ground state, so it's sitting here at the minimum. And with the laser pulse, we excite the iodine molecule to this excited state. Now this excited, and now the nuclear wave packet sits on this new red potential, and now the minimum gets at a different position. So after the excitation, this will trigger a vibrational motion where the bond length oscillates around the new equilibrium position because it's initially displaced. So we excite here. Now the minimum is here, so this creates a vibrational motion like this. And this is a simulation of the vibrational wave packet. So the equilibrium distance in the ground state is about 2.7 angstroms. And here it is displaced to about close to 3 angstroms. But basically what happens is after you excite, you create this wave packet, and then the distance increases to about 3.9 angstroms and then back, and you have now this periodic vibration as the bond length stretches and compresses. So this is the reaction that we want to probe. And again, the basic idea is this: as the distance between the two atoms is changing, there will be some changes in the diffraction pattern, and this is what we would like to capture. So here is a difference diffraction pattern, which is average over 500 femtoseconds. So this is about one period of the motion, which is 400 femtoseconds. And the fact that you see something means that the bond length is changing. And in fact, this matches quite well to the simulated pattern. So we have a simulation of the dynamics, so we can simulate the diffraction as well. And one thing to notice is that now this difference diffraction patterns, they're no longer circularly symmetric. And the reason is that the laser excitation has a higher probability when the laser polarization is aligned with the transition dipole moment of the molecule, which here happens to be along the axis of the molecule. So the molecules which happen, so the molecules are randomly oriented, but the ones that happen to be in the direction of the laser polarization get preferentially excited. So the excited molecules are actually aligned with a fairly broad distribution, but they're aligned preferentially along the direction of the laser polarization. And we will come back to this because this can also be useful to understand more complex reactions. But that's why the diffraction patterns are no longer circularly symmetric. So what can we do? So we are measuring, our measurement is this change in the modified scattering, so this change in the diffraction pattern. But we know what the ground state scattering looks like. We can measure that just by using the electrons without the laser. And here, epsilon is the excitation fraction. So what, for example, here, I think we excite, let's say 5% of the molecules on this, then this would be 0.05. So from this two, we can extract what is the molecular scattering of just the excited molecules. And here's what this is shown. This is the experiment, this is theory. So as we go to larger scattering angles, our signal gets smaller. So so the noise level increases. But you can see quite clearly that this is the diffraction pattern, and once you hit it with the laser, you see these marked changes in the diffraction pattern. You see it also in the theory. So you see this diffraction pattern, and then you hit it with the laser, and you see that the period of the interference is changing, and you can see these oscillations also in the period. Here in the region in green, remember our screen has a hole in the center, so we do not capture the small angles, right? So this is the momentum transfer, and this is time. So the small momentum transfer is not measured in the experiment. So here we only have one pair of atoms, right? So the interference pattern is just one sinusoidal pattern. Now we can, of course, analyze this, and we can do our sign transform, and we can get the bond length. What we measure is the distance, but of course, in this case, this corresponds to the bond length. And now what you see here is now I can display this. Now time here runs down, and now we've converted this to real space. So now we have time running down and the bond length running to the right. So here we start at the equilibrium bond length of about 2.7 angstroms. And then you excite this with the laser, and you see that this increases and then decreases and comes back. And this matches quite well with what we see in the theory. And again, from this measurement, now we can also extract the bond length versus time. And you see that we can quite well capture this oscillation in the bond length. One additional thing is that this measurement, we can see the distance between the two atoms, but we're also sensitive to the shape of the wave packet. And in this case, if the wave packet spreads and becomes broader, and we can also, in principle, detect this with our measurement. So we see not only the distances, but also the shape of the nuclear wave packets. Okay, so with this, we gained some confidence that our method was working, and we had some experience how to do the data analysis. So now let's take a little time to look at a more complex reaction. So this looks still like a simple molecule. It's CF3I, so one carbon atom, three fluorine atoms, and one iodine atom here. And what we look at here is we excite this molecule with UV light at the wavelength of 267 nanometers. And we trigger the bond breaking between the carbon and the iodine atoms. So we want to see what happens when this bond breaks, what happens to the structure. Now, one interesting thing about this reaction is that you start here. Now, again, this is the ground state of the molecule. And you see now we have a lot of excited states. Let me try to explain what is happening here. So the first arrow tells you about what happens if the molecule absorbs one photon in the UV, and you go into this dissociative states. So basically the molecule absorbs one UV photon, and then you go into this repulsive potential. So that means that the carbon iodine bond breaks, and the two fragments, the iodine and the CF3, will just move apart. However, there's another channel where you can absorb two UV photons at the same time, and you now excite to a Rydberg state up here, this yellow Rydberg state. And this Rydberg state can, for example, cross or couple to other lower Rydberg states or these ion pair states. And then from these states, you can dissociate. So this upper Rydberg state is a bound state, but it crosses with other states which can dissociate. And here we got a lot of help from the group of Todd Martinez at Stanford, who did calculations and simulations of what happens in the dynamics. So, of course, this is a multidimensional reaction. So this picture only gives you sort of a cartoon view of what's happening. This one's a little bit better because it has two coordinates. This is just the CI distance. This is the CI distance, and this is the ICF angle. So this angle, and you see this explains things a little bit better. I excite if the molecule absorbs only one photon, it just goes down here and dissociates. If it absorbs two photons, you start on this state, which is bound, meaning the bond doesn't break. But there's this other state which crosses. This is the ion pair state, and from this you can go to a lower Rydberg state where you can dissociate, or you can continue on this state where it also dissociates. So you see that once you're in this upper state, the wave packet can either stay up here or it can cross down to this other state. So this can split the nuclear wave packet in two parts. So now there are two channels to the reaction, and we can separate these two in the analysis. One reason we can separate them is that they happen on different timescales. The direct dissociation from the one photon channel happens faster, and the second channel, where the wavelength is bound and then dissociates because it has to go through all these states, it happens a little bit slower. The second reason we can dissociate it is because the one photon excitation has a transition dipole moment along the molecular axis, and the two photon excitation happen preferentially in the direction perpendicular to the molecular axis. So we can use this to look now at the angular dependence in the diffraction pattern. So for example, this is our difference diffraction pattern. And if we do a Fourier transform and Abel inversion, now we basically get a pair distribution function as a function of angle. So for example, if we plot this in polar coordinates, we can look at the distances which are in the direction parallel to the laser polarization. So this would be this. And we can look at the ones that are perpendicular to the laser polarization. So we can use this to disentangle these two different reaction pathways. So if we now focus first on the one photon channel, and then now, because we have this structurally sensitive information, I can look at the specific distances. And here we're looking in red at the changes in the bond length between, no, sorry, not the bond length, just at the changes in the distance between the fluorine atoms and the iodine atom. And this blue one is the change, this is the bonded distance, carbon, iodine, and we look at changes in this distance. And what you see is what you would expect for dissociation. You break the bond and this increases, and these two distances will decrease. So after I remove the iodine atom, I no longer have either of these two distances. So you see this decrease, which happens very fast on a time scale of 200 femtoseconds. But interestingly, the carbon iodine distance disappears before the fluorine iodine distance disappears. And this was a little bit puzzling why they did not disappear at the same time. But actually, if you think about what is happening, you come with a laser and you break the bond. Basically means you now have a repulsive force between the carbon and the iodine atoms. But the iodine atom is a lot heavier. So if there's a force between these two, and we know that the lighter atom is the one that is going to pick up more acceleration. So what happens is you break the bond, and the carbon atom moves quite a bit more than the iodine atom. So if I move the carbon atom only, for example, this distance does not change much, but the fluorine iodine distance does not change much, which is this one, which lives a little longer, but this one starts to change immediately. And so basically what we see here is the effect of the recoil force on the carbon atom, and the carbon atom gets pushed into the fluorine atoms. This is, of course, an exaggeration of what happens, but it gets pushed in, and then this triggers this umbrella motion now in the CF3 fragment. And what you can see here is a change. So this CF3 fragment, it's vibrating like this, but this vibration is very fast. But there's still a change in the average angle, and this is what we see here, that the average angle increases by about 3 degrees, and the bond length increases by about 0.02 angstrom. And so based on this, we can make a movie. So as this dissociates, right, we see this average angle and the average bond length changes, and this is what you see in here. So this is a movie based on the experimental data, where we see the dissociation and the change in this bond angle. Okay, so now let's talk about the second channel, which is this more complex channel. So here I have another picture where I show only, this is a simplification, but it shows the most relevant states. So I excite here to this state. Now the molecule Now this increasing here is the carbon iodine bond length. So molecule can stay on this upper state where it's bound, and then the bond length will just periodically increase and decrease. So this triggers a vibrational motion. Now, every time the nuclear wave packet goes through this other state, there's some probability that it's going to cross to this lower state and dissociate. So, and remember, we can look at the amplitude of the signal at specific distances. So let's say we look at this one, and then what you see is you start here, and then if some of the molecule dissociates, you would see a drop in the signal. But if some of the molecule stays on this bound state and come back, you would see a periodic increase of the signal, and every time it dissociates, there's a step. So in blue here, we have a look at this. What is the amplitude of the signal at the equilibrium distance? So this is around here, and you see that we start here, and when we trigger the reaction, we immediately see a drop as this wave packet is moving away from this position, moves away from the position. So the distance decreases, and then we see this little revival where it comes back periodically, and that's the part that is trapped on this upper state, and then some of it comes back, but some of it already dissociated, so it never comes back to the original state. Now, we could also look, for example, at a distance around here, and now we know if the wave packet moves from here to there, there should be, so when the wave packet is here, it's not here, and when it is not here, it can be here. So the phase of these two signals should be opposite. So, and this is exactly what you see here in the red. When this one is at a minimum, this one's at a maximum, this one's at a maximum and a minimum. And so basically this means that what you see is this oscillation here and the wave packet moving from here to there. And then also you see that after a period, the amplitude of this signal also drops because you go around in one period, and then when you come back, some of it can dissociate. So this is very clear evidence for the sort of the splitting of the wave packet between some fraction of the wave packet goes to dissociation, some fraction remains here and vibrates on this bound state, and at every period, some more of it couples to the dissociation. And we can also look at other distances. Here's the distance between the fluorine and the iodine atoms. And although less marked, you also see these oscillations here. And you even see this little revival here after 500 femtoseconds. So we also have, as I said before, detailed simulations of this. And this is the simulation at the corresponding distances. And you see that the features reproduce quite well in the oscillations. And then this feature at 500 femtosecond, which we could not explain from the experiment alone, also appears in the theory. So we can look at the theory and try to understand what is happening here. And for that, I'm going to take you on to this plot here. So here, what we are doing is we are looking at it. So this is the pair distance. So this is the nuclear wave packet, and here time increases up. And the color coding tells you about the electronic state. So for example, the initial Rydberg state where you excite is here in yellow. So you start in this Rydberg state, and then as you cross, right, you can cross to this, through this ion pair state into the lower Rydberg state, which is blue. And at every vibrational period, some of the wave packet leaks out into this lower state. And you see the amplitude, there's a vibration in the upper Rydberg state, which decreases in amplitude. But this some fraction of the wave packet that splits can also come back into as a vibrational wave packet. And you see that the ones that split here and here, they both come back at around the same time at 500 femtoseconds. So this is the increased amplitude from two splittings of the wave packet that come back at the same time. And you see that here in the experiment, you see that here in the simulation. And now in the experiment, the region that we can access in the experiment is more limited, but you can see here clearly the splitting of the wave packet here, and then the recombination of multiple splittings, which come back around 500 femtoseconds. So we get very good agreement between the experiment and the theory. And so basically, to give you sort of a cartoon picture for what we see, is you start with the state, and after you excite it, the bond length increases, and then the wave packet splits in two. And one fraction of the wave packet continues to bond breaking, and the other fraction, so one fraction of the wave packet you get bond breaking, and the other one you're in a bound state where the bond doesn't break. So you create this superposition state where the bond is broken and is not broken at the same time. And again, we can see this clearly in these oscillations in the diffraction signal at specific distances. So basically, we now know that we can look at these complex reactions, and we know that we have a tool to look at this. And so the key advantages of this method are that we have temporal resolution, so we can see things in time, in femtosecond scale. We have spatial resolution, so we measure changes in the bond lengths of less than 0.1 angstrom. And we have also angular resolution, meaning that we can extract information from the directionality of the different bond lengths after the excitation. And I should say that so we've been working on this setup since around 2015, and in 2020 this has now become a user facility. So that means that anyone who's interested can submit a proposal and do experiments at this facility. And the first round of about 20 experiments took place at the end of 2020. And these are some of the references of the works that have come out of this instrument in the last few years. If you're interested to read more, the two in blue are the ones that I've talked about today. And with this, I'd like to acknowledge and thank all the people that helped in this research. So my group at the University of Nebraska and the team at SLAC MEVUD, who we've collaborated with. We collaborated with people at Stanford Pulse Institute, Potsdam University, and also our theoretical support from the group of Todd Martinez at Stanford. And this research is supported by the US Department of Energy, Basic Energy Sciences. And with that, I'd like to thank you for your attention.
Sir, for your wonderful presentation. It's a great webinar with you, and I think our students have learned a lot of things from this webinar. So we have got few questions. If you allow, we can start our discussion session. So
Okay.
first question: what is the Rydberg state?
So the Rydberg state is a higher line electronic state where where the energy is quite high but still below the dissociation energy. So basically you excite the electron and it's not quite far from the nucleus. If I stop sharing, can I see people or no? Hello? I lost the audio. I can't hear anything.
So, okay, thank you. This may be the last question. What is the space charge effect?
So the space charge effect, so when you generate a pulse of electrons, so the electrons are charged, so they repel each other. So if you try to make a very short pulse of electrons, the electrons are very close to each other, and so the Coulomb force is quite large. So this basically means that they push on each other. So if you have a short pulse, it's going to spread out. Yeah, this is what we call the space charge effect.
Okay, thank you. So as we don't have any more questions, so we should conclude our discussion session. So thanks for accepting our invitation, and thanks for giving us this opportunity to arrange such an important webinar on ultrafast imaging and molecules with atomic resolution. So we'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitation, sir. So thanks again. Bye for today.
Okay, right. Thank
Have
you.
a nice day, sir.
Thank you.
Bye.